Okay, thank you very much, Al. I'm really sorry. It's just that when I'm sharing my screen, the usual record button that I always use gets hidden by the share screen, and I completely forgot about it. Okay, so I'm not to start again. I'm sorry for people from YouTube. I just gave a very basic introduction. So let's get on with, okay. So I take this occasion also to remind you that yesterday I sent, together with Tera, a survey for getting feedbacks about the summer school. One of the feedbacks, very interestingly, was asking us to include in the next summer school a couple of lectures showing explicit calculations for transition amplitudes. And well, to that person, that's what this lecture will be about. So there's one lecture about that also in this summer school. Of course, you could not know that in advance. I want also to say, everybody, that I'm really sorry for the poor quality of my pictures. So be prepared that in my slides, there will be a lot of happy little accidents. So, because there are no mistakes. So let's start with the review of who, what, and where people are doing numerics in loop quantum gravity. So first of all, I want to review the work that I'm involved in that is concerning the I-said-to-C-form and I-said-to-C-form next libraries. This is a work that has been going on for the last 3 years, almost 4, mainly here in Marseille in the quantum gravity group. The basic idea behind this project is the so-called divide and conquer. And with that, I mean, to compute the spin-form amplitude, we divide it in very small pieces. We compute each one of them, and then we reassemble everything at the end. The library is high-performance computing ready, meaning that it's highly parallelizable, and it has been already used on clusters. So it's not like it's not just a laptop code. It's very fast and efficient. Unfortunately, its main limitation is that some truncation are needed to get a result. I will, of course, be back on this later in the second part of the talk. And since a truncation is needed, we need to estimate the error that we make doing this truncation. Unfortunately, for the moment, the only way we have to estimate the error is empirically. We should find a better way to do it. And the code tends to be computationally quite expensive for large triangulations. There are already some preliminary results on single vertex computation, free vertices, and bubble divergences. Who are the people that are involved in the development of this work is myself and Giorgio Sarno for the very first version. The second version, the I-said-to-C-form next version, is mainly a child of Francesco Gozzini, that is a PhD student here in Marseille. And now the code has been adopted for use and further development by Francesca Vidotto, Carlo Revelli, Pietro Paolo Frisoni at Western University in Canada. And I will leave in the slides the references to all the papers and the libraries. However, we are not the only ones that are doing numerics. So it would be bad for me to not mention everyone else. This is not a self-advertisement talk. It's a lecture about more or less what's going on. Then, of course, in the end, I'm going to talk about my work, but I want to mention everybody else because the community is understanding that numerical work is going to be important in the future of loop quantum gravity and spin forms. So in particular, let me mention the very nice, very interesting work done by Mushin Han and collaborators, mainly in Florida Atlantic University and Fudan University. And I don't remember where Honggang Liu is right now, but I'm sorry. I think Erlangen, if I'm not mistaken. So their approach is very different from ours. They also compute spin form amplitudes. They use Markov chain Monte Carlo computation. The problem is that the way the spin form amplitude is formulated is not suitable directly for a Markov chain Monte Carlo computation. So they need to use some advanced techniques. So they need to deform the integration path on the complex plane using deforming it to a Lifshitz spin ball to avoid exactly this kind of oscillations that are characteristic of the spin form amplitudes. The main success of their approach is that huge spins are accessible, while with, for example, our approach, they're not. However, the price that you have to pay that it works less well for small spins. And I leave you here the link to their main paper about the subject. There are two other approaches that I want to mention very, very briefly. One, because you already had 2-hour lectures yesterday about effective spin form models. It's also a very recent approach, mainly developed by Hal, Bianca, and Seth at Bard College and PI. And so let me also remind that after this lecture, I'm going to send everybody a survey asking if they want to participate to hands-on numerical experiments next week that Hal is organizing. And the other approach is about renormalization and fixed points. So there's a group mainly by Benjamin Bard and Sebastian Steinhaus and students that are based on University of Hamburg and Jena in Germany. And they study the presence of fixed points under coarse graining of spin forms. Of course, with some approximation. In particular, they use a truncation of spin forms amplitudes made only by hypercubes. And I also leave here some references in case you're interested. Okay, so let me start with the first part of the talk about actual numerics. And let me start with the Ponzano-Regge model. Once again, we already saw the Ponzano-Regge model at least 3 times right now in this school. First from Maite, then it was named and used also by Valentin, then a little bit of it, especially from the classical point of view, by Hal yesterday. But I strongly suggest you to read also the original paper that is beautiful. I leave you the link here. It's very difficult to find, so I scanned it, and there's a PDF copy attached to this lecture. You just need to click on the link of the slides. You can just download it. So the Ponzano-Regge model gives or provides transition amplitudes for Euclidean 3D loop quantum gravity. In particular, 3D loop quantum gravity is the boundary of lives at the boundary of Consonant transition amplitudes. In 3D loop quantum gravity, you restrict your spin network states to be 3 valence. Of course, spin networks are are supported on oriented graphs, where you color with SU2 irreducible representations, also known as spins. At the nodes, you put intertwiners to have gauge invariance. The spins are eigenvalues of length operators, of the length operator. Therefore, lengths are quantized because the spectrum of length operator is discrete, is the Casimir of SU2. So, in the nodes, at the nodes, you associate trivial intertwiners. Trivial because they are elements of one-dimensional space. And you can think about them, since as Maite already explained in length, they are essentially Clebsch-Gordon coefficients, or as we like best in loop quantum gravity to describe them, as Wigner 3J symbols, just because they're more symmetric than Clebsch-Gordon coefficients. But if you are more familiar with Clebsch-Gordon coefficients, you can think about them. The nodes of the 3D spin network are usually associated with a chunk of spaces that are dual to triangles. And the closure of these triangles, so the fact that actual triangles, can be interpreted as a consequence of gauge invariance. This was explained very beautifully, I think, yesterday by Hal. So each node, as you see here, you can think about it as a triangle where the links are dual to the edges or the segments, if you want, of this triangle. And the spins somehow measure the length of these triangles. And the node is dual of the triangle itself. So you can think about a 3-valent spin network as a quantum triangulation of a 2-dimensional surface, 2-dimensional surface that possibly could be also curved. So Ponzano-Regge model, the Ponzano-Regge model gives you a recipe if you want to compute transition amplitudes for 3D Euclidean loop quantum gravity. And now I want to spend at least like 10 minutes telling you how to write and build these amplitudes. So first of all, first of all, choose a 2-complex dual to a 3D triangulation. 3D triangulation made of tetrahedra glued together, and the 2-complex is made of vertices, edges, and faces. So the vertices are dual to tetrahedra. The edges of the 2-complex are dual to triangles, and the faces are dual to segments, and the faces are a closed loop, if you want, following edges connecting different vertices. So given a 2-complex that is made like this, you can write the amplitude, but before writing the amplitude, let me change a little bit graphical notation, because red dots, blue sticks, and yellow polygons are not really that useful. So let me represent the faces of the spin forms with wires. Each vertex, since it's dual to a tetrahedra, has four edges that here are represented with these boxes, and each segment is dual to a face that here I'm representing with a wire that is connecting two boxes, so two edges, because each segment of a tetrahedra is shared by two different triangles. So this is if you want, this is whole vertex is a tetrahedra, each box is a triangle, and each line, each wire here is a segment. Ignore for the moment the spins that I put here. It's just that I copy pasted this picture from the next slide, and I forgot to take out the labels. So I don't want to insult your intelligence, but I think that especially for people that are not following live, having one slide where SU2 stuffs are summarized, I think is useful. So let me go through it like in 30 seconds. You know very well that irreducible representation of SU2 are given by spins. I will denote with dj of G the group matrix elements, the matrix elements of the group element G in the representation J between the states M and M, Jm and Jn. In general, to do numerics, you need to pick a parameterization for the group to do the integrals explicitly. The way I usually, the parameterization I usually use is the Euler one, that is just given by three angles, just telling you that a general SU2 elements is a composition of three specific ones by just varying these three angles. And more, in addition, this explicit parameterization let me also write an explicit formula for the matrix elements. So these are not just abstract objects. I can give you a formula for them. In this, if you parameterize the group element in this specific way, this is the formula. We will not probably need it. It's just for references. And to do the integration, you use the Haar measure. And this Haar measure is usually an abstract thing in our mind. It's just the unique left and right invariant measure over the group. But the thing that I want to stress for the students is that is given a parameterization, so given a parameterization of the group elements, it has a very specific form. I will refer to these two texts. One is a very beautiful paper by Pierre, where he just summarized a lot of these things, a review paper. And the other one is the Varsalovich, that is literally the sacred text for SU2 computations. Okay, so we left that we fixed two complex, and let's consider a vertex of the two complex. And this is the recipe to write the amplitude. So for each vertex, associate a group element to each edge. So there's a group element in each one of these boxes. In a second, I will go through. Okay, these are typos. They should not be here. They're clearly errors. Ignore them, please. So there's a group elements at each x, at each edge, and for each face, so for each wire, you associate an SU2 irrep, so a spin, So these are the spins. And a matrix element given by the Wigner matrix of the product of the group element, the source at -1, and the group element, the target. This I'm implicitly saying that you also fix an orientation, as Maite also explained you the first week. I remember there was a question asking what's the interpretation of this orientation? Is it important? Not really, as long as you are consistent with your own choices. It's just saying that these group elements are representing holonomies, and the holonomies are from a point to another point. So these holonomies are telling you how to go from the reference frame of this triangle, so this edge, to the reference frame to this other edge in this direction. If you want to go back, just take the inverse. Then you integrate over all the group elements. You sum over the internal phase with a weight that here unfortunately disappeared. I'm really sorry, but it's just the dimension of the representation. And yeah, this is for me to remember to tell you about this interpretation because the one that I like the most. So what is the vertex amplitude telling you is just how to move from a reference system to the other. You have to imagine that each triangle defines its own reference system. The group elements are telling you how to change from one reference system to the other. And the vertex amplitude is just averaging or integrating over all the possible way you have to change reference system from one to the other. So let me go through this recipe one more time, but doing it explicitly step by step. I will just not write the magnetic indices just for simplicity, just because it's very cumbersome to write them all. So let's associate a group element to each edge, for example, A, B, C, D. I colored also them for easy correspondence between the formulas and the picture. Associate a reducible representation or a spin of S to each face, G1 to G6 in this picture. And for each face, write down the matrix element following this recipe. So for example, take this face, J1. J1 goes from the edge D to the edge C. So as you can see here, I just write the matrix element in the J1 representation of GD to the -1, that is the source, to GC, that is the target. I don't know these things where are coming from. I'm really sorry. So the next step is to integrate over all the group elements. So we have 4 group elements. Let's integrate over them using the hard measure. That's it. That's the expression that you get for the vertex amplitude. So how do you compute it right now? Well, first of all, you split all the representation. You write the explicit formula that I gave you like a couple slides ago for the Wigner matrices, the explicit one. They take the sums over all the magnetic indices. You do the integrals. Yeah, very nice. So this in theory. In practice, this is the worst possible way you can do this calculation. So that's not how we will do it. The best way is to do the integrals analytically as much as you can. Why? Well, mainly because these Wigner matrices are very fast oscillating functions. and do the integrals numerically, it's a pain. You will see a little bit of this probably later. Okay, how do we do the integrals analytically? Well, we know that the integral of the product of three Wigner matrices in three different representations is given by the product of two 3J symbols. Remember, these are essentially Clebsch-Gordon coefficients. Or if you want graphically, we represent the integral of this group element here. So the integral of this box, you can imagine it as the box disappear and two nodes appear. Each node, so each of these three-legged object here represent a 3J symbol. When I glue them together, I mean that I'm summing over magnetic indices. Okay, so if you want to know more about this, go ahead and look at it on the Varsalovich. Could be a little bit daunting because the book is huge, but there's literally everything you need to do every possible computation in this way. Okay. Oh, sorry, let me restart. You see, there's no, I don't know. In the slides, there's no extra objects here, but for some reason, when I do the full screen, sorry, can someone?
Hi, Pietro. Can I ask a quick question? You say that you assign a single group element to each edge, right? Which will be G of E. But then you say that you write the matrix elements in terms of two group elements, G, S inverse G, T.
Yes.
Right. And so, I mean, from from my understanding, like the gauge transformations act at the vertices, right? So I would think of GS and GT as some gauge transformations, and I would write D, the matrix D, as a function of G of E. So, like I'm a little confused. What is the relationship between G of E, G of S, and G of T?
Are you asking what happens under gauge transformation of this?
No, I'm just asking, like, I mean, you have a group element GE, which you assign to an edge, GE.
Yes.
And then you have these group elements GS and GT.
Yes.
So what is the relationship between GS, GT, and GE?
So in general, they're all independent. You're integrating over them. So the full expression at the end is completely gauge invariant in the sense that if I perform a gauge transformation of one edge, this will produce a group element, if you want, on the left and on the right of the box, that then is completely reabsorbed by the others, because you see, you have a single group element that comes, for example, let's do a gauge transformation A, okay? So this will produce group elements here, here, and here. And you say, yes, but then if I want to reabsorb them with a change also in D, C, and B, how can I do it? You can do it by just popping out a group element on each one of the D of the representation matrices containing B, C, and D, and by just noticing that the way they are contracted, the group elements between the extra group elements between BD, BC, and CD cancel exactly, because they're all canceling inside, if you want here, the expression of the amplitude. And then the extra ones cancel exactly the group elements coming from the gauge transformation of A.
No, okay, that's fine. But I mean, what happened to the group element G of E, which you assigned to each edge? Where did that go? Like, that doesn't seem to show up anywhere, right?
You mean
If you go back a
G
couple
here?
of slides. No, if you go back a couple of slides.
Yes.
Yeah, so see, for each edge, one group element.
Oh,
right?
sorry. These GER, the GS and GT. I'm just saying, yeah, sorry. There's.
So this is equal to GS inverse times GT, right?
No. That was probably my mistake. I used the wrong language. I'm saying that the GS and GT are exactly the GE that I'm writing here. For example, GS is one GE, and GT is another one.
Right, got it. Okay.
Following exactly, for example, this way, the GE in the edge A is GA, but then when I need to write the matrix element for the faces, A appears once as target and twice as source. So appears once as target here and twice as source in J5 and J4.
Okay, no, thanks. That was my confusion. Thanks.
Okay, sorry. I used a different letter because I don't know. Because that's the way I'm used to writing without thinking too much about it. I'm really sorry if this made confusion. So, by the way, I'm sorry about this graphical glitch. I don't know if you can see it. For example, here, but on my slides, there's no graphical glitch. But then when I go full screen, it appears. Is it just for me, or you also see this?
We see it too, Pietro, but I don't know why.
I really have no idea. I'm sorry. I thought it was my mistake, but clearly it's Google Slides that is going crazy. So I don't know. If I think that is important, so give me like 1 minute. Can I? No, sorry. Can I export it in PDF and change the software? Download, yeah, PDF. Save file. Okay. So let me switch to the other thing. I'm really sorry, but it drives me crazy. Let me share my screen again. Okay. Okay. Now, of course, there are other problems once it's exported, but I prefer that there's a right symbol slightly off-center than that there's a wrong one. I'm really sorry. Okay, so we were here. So let's do these integrals analytically. When we do them, we obtain 3J symbols contracted together on the magnetic indices. And the result is the so-called 6J symbol. This is another SU2 invariant that graphically is usually represented this way. So it's just 4 3J symbols contracted together. Or usually you find it written in this way with just one symbol with these brackets and the 6 pins involved. There are many explicit expressions for these 6J symbols. For example, as a contraction of Clebsch-Gordon coefficient or 3J symbols, or for example, in terms of sums of factorials, or in terms of hypergeometric functions, or whatever you prefer. There are literally a ton of them. I always refer to this book for almost every expression that exists. But how do you compute these 6J symbols numerically? Well, there are 2 options. One, you code your own function. 2, there's no need to reinvent the wheel. and use softwares that are already written by somebody else. For example, in Mathematica, the 6J symbols are built in, so you don't need to install anything else. You just ask for the 6J symbols and it just gives you back the number. If you are interested in C, Python, MATLAB, or other languages, please use this library here. This was like a very nice finding by us, literally saved us a lot of time. It's library to compute 3Js, 6Js, and 9J symbols done by this, is it Danish? No, yeah, probably Danish group. And this is what we use in our code. And in the school website, I provided with three Jupyter notebooks. So they are Python notebooks, just to show you that it's possible to do this kind of numerics also with programming languages that are very simple to learn. So there's almost no need to go crazy with C or fancy programming languages that are usually not very suited for numerical computation because Python as an interpreted language is very slow. The trick here is that the majority of the computation is done by the library that is coded in C, and the result is parsed in Python. That's the trick. So, yeah, I was saying, in the school website, you find 3 Python notebooks that you can use to explore how to do numerics computation in the Consonant model in Python, for example. And I will go through these 3 basic results that I think are very interesting, also because they prepare the path for what I'm going to tell you later with a way more complicated Imperial model. Okay, first, the asymptotic of the Consonant vertex amplitude. This is one of the nicest results. The original paper by Ponzano and Regge was also mentioned by Maite, I remember it, and is the connection between discrete 3-dimensional Euclidean gravity, also known as the Regge calculus, and the large spin limit of the 6J symbols, the vertex amplitude of the Ponzano regime. So what's this result? If you take the 6J symbol and you look how it behaves under homogeneous rescaling of all 6 spins. So here I introduced explicitly a scale lambda. So lambda is an integer. And if you rescale all 6 spins with lambda, so you fix the 6 spins. In this explicit example, numerical example, I fix all to 1, for example. And you take increasing values of lambda, asymptotically, meaning that for lambda infinite, the 6J symbol is well approximated by 1 over lambda to the power 3/2, the square root of the volume of the tetrahedron that you can build using these 6 spins as edge lengths, as lengths of the segments of the tetrahedron. On top of that, there's also a cosine here, so there's an oscillating factor, and the frequency of oscillations is related to the Regge action that was also explained to you in the lecture yesterday by Seth and Hal. in great detail. So it's the sum of the lengths, so the spins, times the associated dihedral angle. So it's the angle between the two triangles sharing that particular edge. And then there's a phase factor that is pi 4. That is what it is.
Pietro, there's a quick question. It's under which criteria are the J sub I chosen?
Okay, so you can pick the spin as you wish. The formula is valid if and only if these spins actually are the lengths of an Euclidean tetrahedron. If you cannot build an Euclidean tetrahedron with such lengths, then the amplitude is exponentially suppressed. If you can build this tetrahedron, then this is the amplitude goes power law and oscillates with a frequency that is related to the rejection. I hope this answered the question. This allowed Ponsano and Regge to make a very nice analogy with the path integral for quantum mechanics, saying that, look, my spinfor model, they were not calling it spinfor model, but let's use modern language. So the spinfor model that we just built is such that in the large spin limit, if classical geometry, so if a classical path compatible with this boundary data for this, here I'm considering just one vertex spinfor. So if a classical path exists that is compatible with my boundary data, so these 6 spins exist, then the amplitude has a power law behavior, and this V, sorry, I forgot to say, is just the volume of this tetrahedron. If no such classical path exists, if no such classical geometry exists, then the amplitude is exponentially suppressed. So the idea is that the path integral intended as spin form is actually dominated by classical geometries that are compatible with the boundary data. In some way, in some fascinating way, resembling what happens in quantum mechanics, so in the path integral formulation of quantum mechanics, where the semi-classical limit is dominated by classical solution of the classical equation of motion, or the classical theory underlying the quantum system that you are observing. Okay, so the first thing that I want to do is to verify this formula. And to do that, I want to use numerics. So here I made an example. So I fixed all the spins equal to 1, and I plotted the amplitude. So this is the actual value of the 6 symbols for varying lambda from 1 to 100. Okay. It's not very easy to see the similarities between this picture and this asymptotic formula. So let me multiply the numerical data by this factor here in front. And what you get is the following. Oh, this is very promising, because you see now all the data points oscillates between -1 and 1. This is exactly what you expect. So there's an extra factor 2, sorry, from this expression. Oscillate between -1 and 1 that is compatible with the cosine behavior of this term. It's just a sum of an exponential and its complex conjugate. So this is a cosine up to factor 2. So this is oscillating between -1 and 1. So has very high hope. There's very high hope for this to be a cosine, in particular, a cosine that should be oscillating with this frequency. That is, in this particular case, 11.45. So wait a second. Here I'm plotting data that are discrete data with an interval of unity between one point and next to the other. And I want to fit it, or someone compare it with a signal, a cosine, that oscillates with this frequency. This is way higher than 2 pi. So this signal oscillates at least twice for each unity. So doing a fit or a Fourier analysis or whatever you think will not be successful, mainly because you are sampling this signal not fast enough. So the sampling, the oscillating function is way too fast for the sampling that you're using. So the best way to do is just to plot this function on integer values. And here I plotted it using these red squares. And you see that this formula is intended to be asymptotic, meaning that there's literally no reason for very low lambda for the vertex amplitude to be well approximated with this formula. This formula is valid only for very large lambda, ideally infinite, but let's say very large. And you see that this agreement improves very fast with growing of lambda. Okay, so this is a very first result by Ponzano and Regge that we could verify numerically very easily. This is literally 10 lines of code. Okay, we can now try to do something else that is a little bit more interesting. One single vertex is very easy. Let's try to glue more than one vertex together. For example, let's consider this two complex. This two complex is dual to the following triangulation. So you take one tetrahedra. This corresponds to the first vertex that I circled here. Then you glue along a triangle another tetrahedra. Then you glue the last tetrahedra along another triangle, the second one, but also you glue it to the first tetrahedra along a different other triangle. You don't have to imagine this gluing to happen in 3 dimensions. This is just an abstract gluing. You're literally identifying faces if you want. And the dual two complex are 3 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. 10 faces, 9 of which are boundary faces, and 1 of which is a bulk face. So it's an internal face that here I highlighted in red. And at the level of the triangulation corresponds to the segment that is shared by all 3 these tetrahedra. So all the 3 vertices. So you apply the rules that I tell you, the recipe that I told you before, and you get this this expression here for the amplitude on top. This 2x plus 1 was the dimensionality factor that was like glitched before, and I told you in words that there's a dimension of the representation associated with the bike face that you need to add when you sum over all the possible bike spins. So here, if you want to interpret this geometrically, you have 3 vertices. So you have 3 tetrahedra, that very loosely you try to glue together, sharing an internal edge, and you sum over all the possible lengths of that internal segment. I keep calling it edge, but I don't want to make confusion. So they're sharing an internal segment, this red one, and you sum over all the possible values of that internal segment. There's an extra phase that comes out just because of the connectivity. If you follow all the recipe, if you follow the recipe step by step, you also get the extra phase. Don't worry about it. It's not that important for what we are concerned. So first step is to look at the asymptotics. So look how this whole amplitude rescale under rescaling of the 9 boundary spins J1 to J9. You see, I just convinced you that the first thing that we need to check is that there's no exponential decaying behavior signaling that there is at least one classical path in the path integral. So there is at least one classical geometry that is dominating this spin-phone amplitude in the semi-classical regime, in the large spin regime. So this is the log-log plot of this rescaling. And you can clearly see that it's following linear behavior in the log-log plot means power law in the normal plot. This plot was generated with this specific choice of boundary spins and a scale that goes up to 200. Then the second question that you can ask yourself is, okay, now I know that there is a classical path, but I know that there is a classical geometry that is dominating this spin from amplitude, but I don't know to which bulk spin it corresponds. Is there a way to find it numerically? Once you know that such classical geometry exists, the answer is yes. And the answer is, let's look at the plot of the summand of the amplitude. So here you have the value of this function here, so -1 to the power x, 2x plus 1, and the 3 vertex amplitudes as a function of x, so the internal spin, the bulk spin. This plot was done for scale 200, if you're interested. But from this picture, it's not very clear what's the dominating contribution. One would be tempted to say, oh, here, look, there's 2 spikes. That's clearly what's dominating the sum. That's wrong. These are not the points that are dominating, because if you look at the sum, these points are basically canceled by these other points. So there's an oscillation that is averaged to 0, unless there are points in here hidden where this oscillation is slower. So if there are stationary phase points. How do we find such stationary phase points? Well, we devised a very stupid technique, but I think it's very powerful. So once you know that they are stationary phase points, you can look at them by using the property that they dominate the sum. So let's put a cutoff on this sum until capital X, and sum until that point, so until that capital X. So let's perform this sum. If the sum is highly oscillating, so the contributions are canceling each other, then you would get 0 until you cross one of these points that dominates this sum, and the sum jump to a certain value. Sorry, I'm really sorry. This plot is not for px, but it's px normalized to the total value. So that's why there's 1 here. So I will fix it for the final version. So you see that this sum, so this plot is clearly indicating us that there are 2 points that dominates this sum over x. So these 2 points are clearly where all the sum is concentrated. Everything else is oscillation and fluctuation that cancels.
Pietro,
Yep.
quick. I just wanted you to know that you're exactly 1 hour in. We didn't discuss whether you wanted a break or questions, but you're 1 hour in.
Yes, I'm finishing this, skipping the next application, and then taking a pause. This is the last slide that I want to do before the break.
Perfect.
So it should be in time. So can we give a geometrical interpretation to these 2 points? And the answer is yes. These 2 points correspond to the exact value of this internal bulk segment, such that the 3 tetrahedra that are given by the 5 boundary lengths plus the 6th shared internal length. So these 2 points correspond to the value of this internal length, such that these 3 tetrahedra actually reconstruct a flat geometry, meaning that you can embed these 3 tetrahedra glued together in R3, so in flat space, Euclidean flat space. And remarkably, this is exactly what we expect from Ponzano-Regge, in the sense that if Ponzano-Regge is a good quantum version of Regge calculus, you should get that the path integral is dominated by the solution of the equation of motion of Regge calculus that are exactly flat geometries. And that's what we are getting back here. So we are very happy with this result. Unfortunately, these do not work well in 4 dimension. But that's what I'm going to talk in the second part of the lecture. And this result in Ponzano-Regge was what really excited me a lot, because from the Ponzano-Regge point of view, let's say the result is not that exciting. I mean, we can extract this result also analytically. There's a way to do it. And we can compare it to a classical theory. On the other hand, for example, in 4 dimension with the Imperial model, we would really like to get something that resembles solution of Euclidean Lorentzian discrete gravity as the one dominating this path integral, but that's not the case. And we are going to discuss this later. Okay, there's one extra thing that I'm not going to talk about, is that the Ponzano-Regge model, as Valentin told you, is divergent, and you can study and fit these divergences also numerically. So let's stop here, ask all the questions that you want, and let's get back like in 5 minutes for the 4-dimensionality stuffs. So if you have any question, you can just unmute yourself or write them in chat.
Can I ask a question? Might not be, again, interrelated, but I just want to make sure I understand understand it conceptually, because
Sure.
so if you see, is what I'm about to say the point of loop quantum gravity / quantum gravity theory, or there's a conceptual difference or fundamental difference? Well, this is what I mean. In 3D gravity, without matter, just pure gravity, we don't have propagating degrees of freedom, right? So
it's a topological theory, yes.
Yes. So if you try to do gravity as a QFT, I don't think it's meaningful to say what's the transition amplitude for pure gravity, right? But here you can see that you can write a transition amplitude for the Ponzano-Regge model, and you actually get, I think it's a closed exact solution, which is 6J symbol.
Yes.
Then you can take the continuum limit and see that it's Einstein-Hilbert action, I think, but for discrete GR. Is that correct?
If you want, yes, in the sense that you get back the classical theory that you quantize. If you want, yes. Some sense.
Okay. So what I'm saying, like, you can actually write an amplitude for 3D gravity using Ponzano-Regge, but if you do it in like a not normal, I mean like a QFT way, then it's meaningless. You can't write an amplitude for pure gravity, right?
Yes, I think so. Yes.
So is this the whole point of a proper quantum gravity theory, that you can actually write an amplitude for 3D gravity, whilst if you're just expanding around Minkowski or something, you're actually assuming a background? And
well, if you want, in a certain sense, yes. I mean, here we are not looking for propagating degrees of freedom. We're really doing a background independent quantization. So in principle, there's no reason not to be able to do it. The fact that the classical theory behind the quantum construction, the quantum theory, is topological, is also reflected at the quantum level, meaning that the Ponzano-Regge model has a very nice property, meaning that the Ponzano-Regge model is invariant on the change of triangulation, meaning that if you fix a boundary, whatever boundary you want, you write the transition amplitude in the Ponzano-Regge model with whatever bulk you want, up to trivial infinities. There are some technical details that one needs to be careful with. But the result of the amplitude that you get is exactly the same, no matter what the bulk is. And this is a reflection of the fact that the theory you started with, if you want, is purely topological.
Yeah.
There's no degrees of freedom.
Okay, thanks.
Rashid, one other comment. I think Pietro said this very clearly, but just so you have it clear in your mind, the 6J symbols themselves are the amplitudes, right? And they're dominated by critical points, right? And the critical points are critical points of the action and the exponent of these amplitudes. And so it's those actions that give you the Einstein-Hilbert action in the limit, right? The amplitudes themselves don't give you the Einstein-Hilbert action. They're amplitudes.
Yeah, sure.
Right, yeah. Yep. Cheers, thanks.
It's 9:10, Pietro, if you want to go ahead. It's been 5 minutes.
Okay, perfect. Okay, let's move to 4D gravity. This is where the things are getting complicated. Okay, so I'll try to give you as much definition as possible without deriving everything from scratch, because 1 hour will not be enough to do it. And also because Maite technically did it. I was here, so I know that she went pretty fast. So maybe not all of you have cleared the construction, but I try to give you the smallest amount of math that you need to understand what I'm computing. So my goal is give the smallest amount of definition to make you understand what I'm computing. So for the gravity, the Imperial model, I refer to the original paper and Carlo and Francesca book for a more organic derivation, or if you want Maite's lecture, or there's also Alejandro Perez's review, living review, that is very good. So the Imperial model defines, if you want, transition amplitudes for Lorentzian 3D loop quantum gravity. What do I mean by 4D loop quantum gravity? What do I mean by 4D loop quantum gravity? I mean that the boundary state of these transition amplitudes are 4D loop quantum gravity states, the usual one. In particular, I will restrict myself, and the original formulation also restricts to 4 valent spin networks. So all the nodes of the spin networks that I'm considering and I'm writing transition amplitudes for are 4 valent, but extension of the Imperial model for general spin network exists, is a so-called KKN model. It's done by the Polish group in Berlin. And so if you're interested, feel free to go and look at it. I'm not going to touch this. I will restrict myself to 4 valent spin networks and the original definition. It's already complicated at that level. You can generalize, gets even more complicated. Let's avoid that, please. Okay. So in 4-dimensional loop quantum gravity, spins are areas operator eigenvalues. So you have a spin networks, there are spins associated to links, and these spins corresponds to area operators eigenvalues. And there's intertwiners at nodes. These intertwiners now are non-trivial. So you need to, the intertwiner space is not one-dimensional anymore as in the 3-dimensional case. So there's some richness in the structure of the nodes. So you need to tell me which intertwiner you pick. So there's a particular way to build these intertwiners. If people are interested, I can go into this. I prepared that one slide, but that slide is mainly for reference, so I was planning to skip it. If people really wants to, I can stop and do it. But the nice thing is that you can interpret these intertwiners in 4-dimension as quantum tetrahedra. So while before it was easy to understand why, given the 3 lengths, you could, and given the invariant tensor, you could associate to it a triangle. Mainly, given the 3 lengths, there's one and only one triangle, and given the 3 reps, there's one and only one invariant tensor. So the two things were nicely corresponding. Something similar is also happening here in 4-dimension, but now the thing is way non-trivial, meaning that if you give me an intertwiner, there are some techniques to find a quantum tetrahedra, but giving me only the 4 spins corresponding to the 4 areas, you span and you describe a whole space of tetrahedras. Particularly, it's a 2-dimensional space, and is the Kapovich and Milson 2-dimensional space that also Hal talked to you about yesterday. So all things together, you can interpret a spin network as a sort of quantum triangulation of 3-dimensional surface to be more precise, is more than just a triangulation. Is what actually is called the twisted geometries in the literature. So there are more degrees of freedom than just a normal triangulation. But I'm not gonna into that. Please refer to the literature for the actual twisted geometries interpretation of spin vectors. So this was the quantum tetrahedron slide that I'm skipping. If someone wants, we can go back to this at the end. Okay, so how do you build the EPRL spin foam amplitude? Well, the recipe is very similar to what we did for the Consonant edge, and you start from a 2 complex, but now the 2 complex is dual to a 4-dimensional triangulation, not a 3D one. The 2 complex is still made of vertices, edges, and faces, exactly as before, but now all the objects making the 2 complex are dual to a geometrical thing with 1 dimension more, meaning that while before the vertices were dual to tetrahedron, now the vertices are dual to 4 simplices that are generalization of tetrahedra in 4 dimensions. While before the edges were dual to triangles, now they're dual to tetrahedra. While before the faces were dual to segments, now they're dual to triangles. So everything stepped up 1 dimension. The vertex is dual to a 4 simplex that I will directly represent with this wiring representation. So I have a 4 simplex that is made of 5 tetrahedra. Exactly has a 1 tetrahedra is made of 4 triangles. So 1 dimension more, there's 1 more of everything. So there are 5 tetrahedra. And each tetrahedra shares with another one a triangle. And there's a total of 10 triangles. Okay, to be able to write the vertex amplitude, I need a little bit of representation of the SL2C. Here, there's way more than what we will need. It's mainly just for reference, if you want to understand more. The 2 places where to learn these things is, once again, Pierre's review is very, very good. And the original book by Rule, I think, is quite understandable. What are the ingredients that I need? Well, I need the fact that SL2C is a non-compact group, and I need the unitary reducible representation in the principal series that are labeled by real number, rho, and spin, an alpha integer, k. Okay, so the matrix elements, exactly as the Wigner matrices for SU2, are given by matrix as a SL2C matrix element. But now, in the representation labeled by rho and k, you can pick a basis that diagonalize a particular generator. Let's not get into that too much, but is labeled by an SU2 representation, J, and the magnetic index M with the usual, these are SU2 numbers. So J is a spin, and M goes between -J and J. The only requirement is that this J has to be greater and equal than K, the spin that labels the representation. So since the group is non-compact, the representation is infinite dimensional, meaning that this J has a lower bound given by K, but there's no upper bound. You can go up to infinity. Okay. A useful parameterization of an SL2C element is given by this Carton decomposition. That is just saying that if you want to represent a general SL2C element, you can make an SU2 rotation in some three-dimensional space, a boost in the in the plane spanned by the last remaining coordinate and the third coordinate of your three-dimensional space that you pick, and then another rotation. This is not really important. It's just to give you an exact formula. If you are not following this part, don't worry about it. It's not that important. I want just to stress that all the ingredients are well defined and we have exact formula for everything, in particular also for these matrix elements that are way more complicated and are given by an SU2 matrix element, another SU2 matrix element, and in between sandwiched, there's this function here that depends on the rapidity defined here in the Carton decomposition. And notice that this rapidity is the only thing that now remembers of the fact that the group in the beginning was non-compact, since both the other two SU2 are compact pieces of this matrix. The non-compactness is just representative of the fact that this R lives in R plus, so it goes to infinity. Okay. So this was just to give you a little bit of math, but don't worry about it. It's not that important. I mean, it is important, but if you're not following, you can forget about it. The details. The only thing that you need to remember is that the Imperial model is defined in terms of the so-called Y gamma map. It is a way to embed SU2 spin network, so SU2 representation, in SL2C ones. And how do you embed them? Well, you take them and you take the SU2 labels, so the SU2 representation, the same, and you pick the SL2C labels, the spin one, you take it the same, and the continuous one, you take it gamma times the spin. I see a question in the chat saying why the change from SU2 to SL2C algebra. Well, the SU2 algebra was the algebra defining the boundary of the spin form. The gauge group of the whole spin form, so also with the bulk, is SL2C. If you go to the boundary, so you imagine that you take SL2C and you restrict to the group that, for example, preserves direction, what you get, so a four-dimensional direction, what you get is exactly SO3 or SU2. So that's why we have an SU2 spin network at the boundary, if you want, and that's what allows us to put or to dress, if you want, an SL2C amplitude, that is the gauge group in four-dimensional Lorentzian gravity. So to dress it at the boundary with an SU2 spin network. And that's what makes the connection between the Lorentzian spin form models and the SU2 loop quantum gravity spin networks description at the boundary. Okay. So the recipe to write the amplitude is exactly the same as before. The only difference is that now, instead of using SU2 Wigner matrices, we need to use SL2C Wigner matrices. So this complicated object that I showed you before, but not any SU2 Wigner matrices, but an SU2 not any SL2C Wigner matrices is the Wigner matrix where we apply this Y gamma map. So where we restricted the representation to be the gamma JJ1. And notice that exactly as before, to do the integrals, we need to split this representation using representation property in the matrix of the source and the matrix of the target, and then do the integrals. when you do that, you not only pick up a sum over the M magnetic index of SU2, but you pick up also a sum over the SU2 spins here, because both these labels are magnetic respect to SL2C. So when you split the SL2C representation in source and target, you not only get the sum over the, here I'm calling it O, magnetic index of SU2, you get also a sum over all the possible SU2 representation in the gamma JJ SL2C representation. Notice that also here technically was true, but is part of the ingredients defining the Y map, is that of this whole tower of SU2 representation, you just pick the lowest one. You just pick the first one, and you throw all the other away. The Y map is imposed only at the boundary, if you want, of the vertex amplitude. And this splitting is happening inside the vertex. So the model do not impose the Y map also here. Do not impose the Y map also on this SU2 index, on this SU2 representation. So we need to sum over all of them. And that would be, I'm stressing this point because it would be critical for the following. So as we did before, we can perform these integrals kind of exactly. That's the whole point of the libraries that I'm going to introduce in a second. No, sorry, I'm reading the question because I had the chat open. There's no problem. We are integrating with the hard measure of the SL2C. In this particular Carton decomposition is just the product of two SU2 measure and the measure in the non-compact direction with this specific measure given by the hyperbolic sign. There's also like a pi here as a normalization that is completely arbitrary because this integral clearly, given that the group is non-compact, is non-normalizable, but let's say it's a conventional pi that usually is put in here. That's essentially the measure. And different questions you can ask is that since the group is non-compact, are these integral convergent? This is a very good question. The answer is yes, but I'm gonna show you this a little bit later. But thank you for the question. This was very important. So the SL2C integrals can be done exactly, more or less. What you get is graphically this expression. So you get a sum over some virtual intertwiners K of 4J symbols. So this is a normal intertwiner on the other side, and a strange object that exactly contains the integration over the non-compact direction that I'm gonna explain you in detail in a second how to compute. But for the moment, let me just do this splitting. So this splitting is just given by, if you want, the integration over the 2SU2 part in the Carton decomposition that I showed you a second ago. And the non-compact integration is just hidden in these bubbles here, in these objects here. This decomposition in spin form was first introduced in this paper. Let me cite it. And as a remark is we are summing over these virtual interpolars. Yeah, so finally, this is the full expression of the EPRL spin-form amplitudes. The intertwiners contracts one each other and gives you back an SU2 invariant that is specifically in this case 15J symbols. while these bubbles here are given by this expression here. We are calling them booster functions because they boost tetrahedrons. I'm going to go back to this in a second. And they're defined in this way. So the message that I want you to take home from this is that the Imperial model vertex amplitude can be written as a linear superposition of 15 J symbols weighted by the product of these booster functions, one per each edge, but one because this is how the Imperial model is defined. Technically, to avoid a trivial divergence, one of the integrals is gauge fixed to the identity to one by hand. So this is an extra ingredient that is given, that is coming from the Imperial prescription. Okay, so how do you numerically compute this mass? Using libraries that we wrote in the last 3 years, expending a lot of energies. So let me very briefly introduce you the two libraries that we use. The first one is SL2C foam, that is the prehistory. The first one that we built is written in C. The SU2 invariants are computed using the big XJPF library that I told you before. It uses arbitrary precision arithmetics because of highly oscillating integrals. And the thing that you need that comes from cancellation, so you need arbitrary high precision, and floats are not enough. It's parallelizable. It was the first attempt that we made. If you want, this was a proof of concept that it was possible to compute these amplitudes numerically. So it's good, but our approach was, let's write something that is good as long as it works. It was largely unoptimized and was quite slow. So next come Francesco Gozzini, that rewrote the library almost entirely with the same kind of spirit, but optimizing all the steps. And SL2C foam next was born. Both libraries are stored in a repository on Git. You can download it freely. There's a paper describing the first one. The second one, the paper is coming, but the library is already available. So feel free to download it and use it. It's written in C, also SL2C foam next. Has some characteristic in common with its predecessor. However, it is optimized to be very efficient. It computes the booster function in a completely different way, and uses a multidimensional array as data structure to store all the pieces. It's high performance computing ready, meaning that he's using is parallelized with the libraries that are supported by clusters. And he also worked on the GPU implementation, so you can use also graphic cards to perform these computations, and has a Julia interface, meaning that if you're not interested in putting your hands inside the code, there's a very nice front end that you can use to compute the amplitudes without caring too much what's happening behind the curtain. And this, just to give you an example of a code written in Julia that is very similar if you want to Python. It's a notebook style programming language. And in like 5 lines, you can compute the vertex amplitude of the spin foam with all spins equal 1. So the Imperial vertex amplitude with all spins equal 1 and all intertwined equal 1, with a certain kind of precision that I'm going to explain in a second. And already at small spins, there was a huge improvements, like 5 order of magnitude improvements in speed compared to the previous version of the library. So Francisco, good job. Okay, so let me explain you very simply how it works. The idea is to divide and conquer. So split in small pieces, compute them, and then reassemble everything. 50 J symbols, well, that's the easy part. We compute them using the VigX library. We just use that. You just use the expression for the 15 J symbols in terms of 6 Js. This library gives you 6 Js. You just sum 6 Js and get the 15 J. Nice. That's the easy part. The slightly less easy part is computing the booster functions. So these bubbles here. It's not that difficult now, but still takes a little bit of work. Notice that the booster functions are quite important because they encode the details of the models. For example, they encode exactly the imposition of the simplicity constraint. If you want, notice that the barbarian easy parameter, that is the one entering and playing a central role in the linear simplicity constraint that are at the base of the definition of the model, just enters in this function here and nowhere else. So these objects are very important. This object also has a very nice and well understood semi-classical limit. We very recently managed to publish finally, after 1 year of no answer from the journal, the paper. Nice. And we already know the result of this integral analytically, and is related to SL2C Clebsch-Cartan coefficients. So to answer the question that was posed before in chat, yes, these integrals are convergent, but the convergence is non-trivial. We know that they're convergent because they're equal to SL2C Clebsch-Cartan coefficient that we know that are numbers. They have an explicit form that you can go and read in this paper if you want, and in the Russian literature in the 70s. However, implementing that specific form of the booster function, so the booster function in terms of SL2C Clebsch-Cartan coefficient, is very inefficient numerically because it's made of a lot of sums of analytically continued gamma function that are very hard to code. Instead, we opted to do the integrals manually, and also connected to the question before, how do you do this integral manually if they are on an unbounded interval? That's basically very complicated to do numerical evaluation of integrals on an unbounded interval. Well, they're not really unbounded because these small function that enters here in the definition that are given by this very complex expression actually are function of e to the minus r. So it's very immediate to map this 0 to infinity interval to 0, 1 by just changing variable to e to the minus r equal to something. That's what we do. So the interval here, this is a plot of this function for some values of the labels written here between 0 and 1. So you see that the function is not that complicated, apart from the fact that it's highly oscillating, and the result of the integral actually is condensed, is contained in cancellations. So to do these integrals, you need arbitrary precision routines, and just the standard C type of long double has not enough precision. So you need to be careful. And the way we do the integral here is just by using an adaptive Gauss-Cronrod quadrature method that is just a method, an efficient method to do a numerical integration in one dimension, not knowing how many points you need to sample accurately enough your function. And also because there's an implementation of this method in GLS, that is the standard library used in C to do math. However, Francesco adapted his own version from the GLS one, doing minor modifications and optimizations. Okay, so now the booster function are completed. So we know how to compute all the pieces numerically. The other part that is tricky are the sums. So I told you, kind of cheating, that the amplitude is a linear superposition of 15 G symbols. Is correct. But not really, in the sense that, yes, if you fix L, you have, so if you fix the spins L, you have precise amount of virtual intertwiner K that you need to sum over, and the sums, we are doing it storing everything in multidimensional arrays, and doing the sums instead of just looping, as we were doing in the first version of the code. That is very inefficient. You do it as tensor contractions, and there are optimized routines to do that. And it's very fast, very efficient, nice. Okay. The problem is that the summation over the virtual spin L that are inside the SL2C representation, that are a consequence of our splitting of the SL2C representation, this sum, as I told you before, is unbounded. So it goes up to infinity. So it's an infinite linear superposition of objects. Okay, how do you perform a numerical computation of an infinite sum? Well, you don't. You need a cutoff. You need to put a cutoff. So we cut off these sums. We cut off it in a homogeneous way. So all the 10 spins here, in particular, there are 6 L's because 4 are gauge fixed. So the 6 sums over L's are all cut off with the same delta S. This is a choice that we made to have it as simple as possible. So the sum goes from the minimal possible spin JF to the maximal one that we fix by hand to JF plus delta S. Now you can ask, well, okay, is this a good approximation? Yes, because we know these sums are convergent, because we know that the vertex amplitude is well defined. People have proved it analytically independently. So we know that this expression at the end is convergent. So putting a cutoff that, as I will call them in the following, is fixing a number of shells. So I'm calling delta S number of shells by imagining it as an onion. When you start by the core, and then you put layers on top. Eventually, is a good approximation. Unfortunately, that's the major disadvantage of our technique. We don't know when is a good approximation. We don't really have a control on the error of the truncation, or the error that we make by making this truncation. This is a bad part. The only way we know how to do this, to estimate this error, is empirically, by just looking at the amplitude and looking how much it changed if we add one more shell. So if we push this cutoff to one more, the problem is that the convergence of these sums looks like it depends on everything, and trying to devise a way to control this error before doing the computation is work in progress, and we don't know how to do it. The strategy for the moment is just put as many shells as you can, as your resources allows you. But you see that for small spins, these are some plots, this convergence is quite small, and you go to, let's say, if you believe that the last value is the convergent one, the previous to last differs from the last one by less than 1%. So you can say, at least for small spins, this convergence is fast. Let me do one application, and then I stop for questions, but I have two more, and they're written in the slides, and you can look at the nice plots. So the first application is to test the asymptotic formula for the EPRL model. I'm not giving you any detail. I'm just giving you the idea here, because giving detail will require me a lot of time that I don't have. And it's enough to say that the situation is very similar to what happened to Consonant region. And if you take the EPRL amplitude and you put boundary states that are coherent states now, because just putting like normal intertwiners is not enough to describe a geometrical three-dimensional tetrahedra. You need coherent states to do that. And that's part of the slide I skipped, unfortunately. On the boundary of your EPRL vertex amplitude, but you put coherent state peaked on tetrahedra that are the boundary of a Lorentzian force simplex, you get a power law behavior of the amplitude plus oscillations with a frequency that is the same of the Regge action of the Lorentzian force simplex. And with these plots, I want to show you that more or less we can confirm this by remembering that the formula is asymptotic. So there's no reason to believe that the agreement is going to happen for small spins, for small scales. It's going to happen for large scales. But let me do it by adding one shell at a time. So by refining my truncation over shells, adding one piece at a time. So where's the power law behavior? Here I factored it out. I just multiplied the power law. So that's why you don't see power law decay. The red band is the asymptotic formula. The blue dots are the data points. So if you put no shells, so delta S equals 0, you see that the agreement is very poor. Why? Well, because the truncation is too harsh, and you will see that the truncation is worse and worse higher the spins are. So more larger the spins you're working with, larger the amount of shells you need to actually have your truncation be a good approximation of the amplitude. If you add two shells, you see that the numbers changed a lot apart from the very first point. That's exactly in agreement with what I just said. If you start adding like 4 shells, you see that the first hint of an oscillation starts appearing. If you add 6 shells, you see that you're almost there. And with 8 shells, that is the amount that we are able to reproduce right now before depleting all our numerical resources, you see that you're starting to see that the frequencies kind of agrees, and there's the beginning of the second oscillation. This is not the second oscillation, sorry. The beginning of the rising to the third zero is happening. Okay, so I have 2 more slides and like a 3 vertex amplitude and infrared divergences that are probably interesting, but I prefer to take questions. Let me skip to the conclusions. So my conclusion are mainly three messages. First, doing the computation with the Consonant model is an excellent way to play around with spinforms on your laptop, meaning that you can do numerical computation on your laptop. You can play around with things, phases, 3 vertices, 4 vertices, 5 vertices. We did all such things. It's very easy. You can do it on your laptop. It's way less. There are way less technical difficulties than for this, but shares a lot of formal aspects. Unfortunately, what you cannot do is to extend the results in a straightforward way from 3 to 4 dimensions. Second message is that we have a well-written, optimized, parallelizable, user-friendly code that is set to see from next, that is ready for use and allows to compute the EPRL Lorentzian spinform amplitudes. The elementary one, you can also do it on your laptop, but to do serial computation, you need high performance compute. Just as an observation, notice that our resources, for example, the computation that I showed you here, takes sorry, I think 1,500 CPU hours. No, sorry, more. It's 10 to the 6 CPU hours with 1,500 cores. And that's the maximum amount we have. However, people that are doing lattice QCD have like 6 orders of magnitudes bigger machines than us. So it's not that we are limited by the technology, we are limited by the technology our money can buy. The field of numerical evaluation of spinform amplitudes is in constant development. So we change idea on how to do things very quickly. The message is that we should not be afraid to do so. This is mainly a message for me, because I'm quite conservative in the way I do stuff. And sometimes you get stuff wrong, as it happened. And you just need to be brave and be able to change idea. So if you want to contribute to this field, you're very welcome to fork the SL2C form repository and have fun. Things to do that are interesting is to implement the Euclidean Imperial Model that has the advantage that the sum of the Virgilta spin is bounded in that case. So you don't have the problem of convergence. You have many terms, but they're finite. So in that case, you can say, I'm not truncating, I'm literally computing all of them. And the only thing that changes is the booster function. You need to call the Euclidean booster function. And very recent, probably very soon, is going to appear a paper on how to formulate the Euclidean booster functions and the Euclidean Imperial Model in terms of booster function. And what's the relation with the Lorentzian one? We managed to find a big rotation, by the way. It's very interesting. If we are not able to push our truncation high enough, is there a way to do an extrapolation from the point we can compute to the limit cutoff on the shell to infinity? We don't know. There are people working on it, especially Pietro Paolo Frisoni and Francesco Gozzini. And we need, now that the code is ready, we need amplitudes representing physical processes to compute. So don't be shy to make proposition of things to compute. In particular, I know that Carlo Rovelli and Farshid Soltani at Western University, and probably Francesca Vidotto, sorry, are using the numerical codes to do computation on bouncing black holes. And that's everything that more or less I wanted to tell you about. And I think I still have 5 minutes left for questions.
Thank you so much, Pietro. Questions for Pietro?
I'm really sorry. There were parts that were fairly technical. I tried to strip down the technical part to the bare bones. Probably were still too technical. I tried to do my best on simplifying things much as possible.
Pietro, I was really interested in this very short comment you made at the end here about a Wick rotation to the Euclidean. Can you give us a preview of that or some idea of that?
Okay, so this is an analytical result. It has nothing to do with numerics, but we were able to prove analytically that if you start that the Euclidean Lorentzian Imperial Model, the vertex amplitudes are related up to a multiplicative factor by an analytic continuation in the Mirzi parameter. So if you take, for example, the Euclidean amplitude and you send gamma to I gamma, you get the Lorentzian amplitude up to a prefactor that we computed. Exactly.
On the numerical side, would this mean that we might be able to access Monte Carlo methods?
Oh, no, because notice that this was a delicate point. So I try to insist as much as possible not to use the word Wick rotation exactly for this comment. And I'm happy you made it. It's a Wick rotation in the internal gauge group. So it's not a Wick rotation of the action as you do the Wick rotation in QFT. But there's a whole literature in this kind of rotation of the Mirzi parameter. Basically, what you do is to rotate the spin for connection to a cell-to-C connection. But you still have an oscillating integral. So you still have a phase as you still have e to the is, not e to the minus s.
It's very clear, yeah. Other questions for Pietro?
Even random question like, do you really think this is useful? Yes, that's my answer. Thank you, Eugenio. So what's the status of bubbles? Okay. So bubbles. People are trying to compute bubbles in the Imperial Model. Particularly, these are the people I think doing it actively. I have more a consulting role, so I didn't put myself in the list. The lead student doing all the work is Pietro Paolo. So what's the idea? The idea is that if you have two vertices connected together, possibly you have divergence. These kind of graphs are called bubbles and are the same kind of bubbles that were studied by Valentin Bonzon and are important if you want to do the renormalization of spin forms. In particular, this is interpreted as a renormalization of the propagator of spin forms that at bare level, if you want, is just the identity. There are analytical results on bubbles. There's first one was by Aldo that gave a lower bound on these bubbles. The second as logarithmic divergent in the cutoff that you put on the faces, in the sum of internal faces. The Second result is by myself, some years ago, and I give an upper bound. However, we still don't know how much they diverge. It's somewhere in between. A numerical estimation is in progress. There are some preliminary results. The problem here is that I don't think we have a high enough amount of shells available to take a conclusion. We just see that are kind of diverging. And this statement is supported by this other graph. That is the difference of the amplitude with cutoff 4 and cutoff 11, both with 11 shell and normalized to the final value. And while you see that I can try to sell you the fact that for cutoff 4, enough shell are 11 shell are enough, is an enough truncation to capture the value of the amplitude. This is not the case for cutoff 11, for example. And that's why I think it's really, really important, if we want to make good progress, to find a way to predict the functional behavior of these curves, parameterize it in some way, use the data that you can produce to fit or this parameterization, and then extrapolate the result. So that's the strategy that's currently in progress. And that's how much I can tell you without saying something that probably I need to change like tomorrow. But I think it's still remarkable the fact that we can numerically compute 2 vertices, 6 internal faces, everything unbounded, up to 11 shells and cutoff 11, so spins of order 11. I think it's very remarkable that we can, because with the original code, we barely were able to put more than 1 or 2 shells. 11 are a lot.
Any further questions from students?
Okay.
Shall we close the session?
Yep.
Thank you, everyone. As you know, Andrea Di Biagio will be giving an overview of experimental results in a half an hour or